Hello everyone. Welcome to chapter 6 for CS 110 at VCCS or Laurel Ridge Community College. My name is Amit Brambhat and today we are going to go over chapter 6, low-level programming languages and pseudocode. Welcome to chapter 6. In this section, we explore how computers understand and execute instructions at the most fundamental level. We'll walk through machine language, assembly language, and the PEP9 virtual machine, tools that help us understand how software interacts with hardware. Later, we'll shift into pseudocode, which helps us express algorithms clearly using structured English. This chapter builds the foundation for understanding how programs really work under the hood and how programmers bridge the gap between human thinking and machine execution. Let's get started by looking at the goals of this chapter and the idea that will guide our journey. Chapter goals. In the first set of chapter goals, we focus on understanding what operations a computer can perform and how the PEP9 virtual machine works. You'll learn to distinguish between intermediate and direct addressing modes, two different ways the machine interprets data. We'll also cover how to write a simple machine language program and understand the difference between machine language and assembly language. Mastering these concepts is essential because they show you how exactly instructions are formatted, stored, and executed inside the computer. By the end of this section, you'll have a solid grasp of how low-level instruction translates into real machine behavior. The second group of chapter goals expand your skills into assembly programming. You'll learn the complete process for creating and running an assembly language program, from writing instructions to translating and executing them. We also discuss how to distinguish between instructions intended for the assembler and instructions that will be converted into machine code. Additionally, this part covers understanding the difference between following an algorithm and developing one. You'll also explore the main pseudocode constructs used to express algorithms clearly and systematically. These skills are essential as we transition from machine instructions to more human-readable algorithm design. In the final set of chapter goals, we focus on designing algorithms using pseudocode and learning how to test programs effectively. You'll use pseudocode to express an algorithm in a structured way, making it easier to translate into assembly or high-level programming languages. We also discussed two major approaches to testing programs and how to design and implement a test plan for assembly language project. By the end of this chapter, you'll have a full skill set, understanding low-level machine operations, expressing solutions in pseudocode, and validating your programs through systematic testing. Computer operations. A computer is a programmable electronic device capable of storing, retrieving, and processing data. It treats data and instructions the same way. Both can be stored in memory. This means program is really just a specialized form of data the machine knows how to interpret. In this slide, we explore the fundamental operations that all computers can execute. These operations form the building blocks for everything computers do, from simple arithmetic to complex software. Understanding these basics helps us appreciate how machine-level instructions work and why low-level programming languages must be extremely precise and structured. Machine language. Machine language is the most fundamental language a computer understands. It consists entirely of binary coded instructions built directly into computers' hardware. Early programmers had no choice but to use machine language because assemblers and high level languages didn't yet exist. Each instruction is represented as a pattern of bits that the CPU's circuitry recognizes and responds to. In this section, we explore why machine language existed in this form and what challenges programmers faced at this very low level. Understanding machine language helps us appreciate the evolution towards more human-friendly programming languages. Machine language has several key characteristics. Every processor type has its own unique set of machine instructions, meaning code written for one processor won't run on another. The CPU's digital logic circuitry is designed to recognize specific binary patterns as valid instructions. Each machine language instruction performs a very small, low-level task, often involving only one simple operation. This simplicity makes machine language powerful but extremely tedious to work with. These limitations are exactly what motivated the development of assembly languages and later high-level languages. PEP9 Virtual Computer. PEP9 is a hypothetical virtual computer used for teaching purposes. It contains all the important features of real machines but is simplified enough to learn easily. Designed by Stanley Warford, PEP9 includes 40 machine language instructions, far fewer than real commercial processors. This makes it ideal for learning how machine instructions are formatted, stored, and executed. Although we won't cover all 40 instructions, we'll explore enough to understand how low-level operations work and how machine processes data step by step. PEP9 provides a safe learning environment for experimenting with assembly and machine languages. PEP9 features. Here, we look at the main register and memory structure inside the PEP9 machine. The program counter PC holds the address of the next instruction to execute. The instruction register IR contains a copy of instructions currently being processed. The accumulator A is used to hold data and computation results. PEP9 also features a large 64 KB memory which stores both instructions and data. Understanding these components is essential because every assembly language instructions interacts with these registers and memory in predictable ways. This slide sets the foundation for interpreting how programs run inside PEP9. PEP9 architecture. This slide introduces the overall architecture of the PEP9 virtual machine. The architecture diagram shows how the main components interact: memory, registers, the CPU, and the input-output pathways. By understanding this layout, we can visualize how instructions move through the system and how data flows between memory and accumulator. This becomes especially important when interpreting instruction formats and addressing modes. As we continue, you'll see how this architecture influences every aspect of machine and assembly programming in PEP9. Instruction format. This slide introduces PEP9 instruction format, which defines how each machine language instruction is organized. The figure shows that an instruction is divided into fields, each serving a specific purpose. Understanding this layout is essential because PEP9 interprets instructions based entirely on how these bits are arranged. Every instruction includes an operation code or opcode that tells the machine what action to perform. Additional fields may specify the register involved or the addressing mode used. By recognizing this structure, you gain insight into how the machine decodes and executes commands step by step. This layout becomes the foundation for both machine language programming and understanding how assembly language translates into binary. Instruction format. In this slide, we look deeper into individual components of the PEP9 instruction format. The operation code tells the computer what operations to perform, such as loading data or performing arithmetic. The register specifier identifies which register should be used. For our purpose, it always indicates the accumulator. The addressing mode specifier is especially important because it tells the machine how to interpret the operand portion of the instruction. This determines whether an instruction will treat the operand as an immediate value or an address in memory. Understanding these elements helps clarify how the machine interprets every instructions and ensures your programs behave exactly as expected. Instruction format. This slide focuses on the difference between immediate and direct addressing modes. The figure illustrates how these modes affect the meaning of the operand. In immediate addressing, the operand is treated as actual data stored right in the instruction. In direct addressing, the operand represents a memory address and the machine must fetch the data stored at that location. This distinction is crucial when writing programs because it determines how the machine interprets and retrieves information. Understanding these modes allows you to create efficient instructions and avoid subtle errors that arise from misinterpreting operand meanings. Sample instructions. Here, this table shows subset of PEP9 instructions. It gives you practical sense of what kinds of operations the machines can perform. The table includes instruction mnemonics, their opcodes, and brief descriptions. These instructions form the basic vocabulary for PEP9 assembly language. By examining them, you begin to see how operations such as loading, storing, arithmetic, branching, and output are represented at the machine level. Understanding this subset equips you with the core tools needed for writing simple programs. As you become familiar with these instructions, you'll be able to translate logical steps from pseudocode directly into low-level operations that PEP9 can execute. Sample instructions, slide number 2. Here we see how to load a value into the accumulator using PEP9 instructions. The example shows both immediate and direct addressing. With immediate addressing, the value appears right in the instruction. With direct addressing, the instruction points to a memory location containing the value. This distinction affects how data is retrieved and processed. Loading values is one of the most fundamental tasks in assembly because nearly every operation begins by placing data into the accumulator. The visual example helps you see how these instructions are encoded and how they behave during execution, reinforcing your understanding of addressing modes and instruction structure. Now, the final slide focuses on adding an operand to the accumulator. Like previous examples, you'll see that addition can be performed using immediate or direct addressing. Immediate mode adds a constant value embedded in the instruction, whereas direct mode adds the value stored at a memory address. This example highlights how simple arithmetic is carried out at the machine level and how the accumulator serves as the central working register. Understanding this instruction helps you write programs that perform calculations and update values over time. It reinforces the idea that even complex computations are built from very tiny, well-defined machine instructions. Writing high. Here you'll see a practical example of writing the text high using PEP9 instructions. The example demonstrates how characters are represented as numeric values and stored in memory. The assembly code loads each character and outputs it at one at a time. This example illustrates how low-level programming handles text. Each letter must be encoded, placed in memory, loaded into the accumulator, and then sent to the output device. While simple, this program demonstrates how assembly connects numeric codes to readable characters and how even tiny tasks require multiple precise instructions. It's a powerful reminder of how much abstraction high-level languages provide. PEP9 Simulator. PEP9 Simulator is a software tool that mimics the behavior of the PEP9 virtual machine. It allows you to enter machine language instructions in hexadecimal, run them, and observe their effects on registers and memory. This slide explains the basic process. Enter the hex code byte by byte, separating the bytes with spaces. The simulator makes it possible to experiment with machine language programming without needing physical hardware. It provides immediate visual feedback, an invaluable feature for learning low-level programming concepts. By using the simulator, you can see exactly how instructions modify memory and control flow. Here, in this example, we see an interface of PEP9 simulator. You can see areas for entering machine code, displays for CPU register, and output windows for viewing the program results. The simulator allows step-by-step execution, meaning you can watch each instruction run individually. This helps you understand exactly how the program and program counter changes, how the accumulator updates, and how memories exist. Seeing the machine operate visually makes learning PEP9 much more intuitive. By studying register changes in real time, you gain insight into how instructions are processed at the hardware level. PEP9 Simulator. This slide provides another perspective on the PEP9 simulator, highlighting additional tools and execution options. The interface might show memory dumps, breakpoint settings, or step controls. These tools help you debug programs by allowing you to stop execution at any point and inspect the machine state. For learners, this hands-on interaction is essential. It helps reinforce the connection between instructions and their effects on memory, register, output, etc. Using these tools, you learn how to trace program flow and diagnose logical or instruction level errors. PEP9 Simulator final slide emphasizes that PEP9 environment fully replicates how the virtual machine operates. You can run complete programs, observe output, and verify whether your instructions work as expected. The simulator gives you a safe environment to practice machine-level programming, experiment with instruction sequences, and see immediate results. This visual interactive approach helps you understand how low-level code transforms into actions performed by the CPU. By mastering this simulator, you build confidence in writing and debugging both machine and assembly language programs. Assembly language. It's a major step up from machine language because it replaces long binary patterns with simple mnemonic codes that humans can read and remember. Each instruction in assembly directly corresponds to machine language instruction, making it a low-level language but far more manageable than raw binary. An assembler translates these mnemonic instructions into machine code that the computer can execute. This slide highlights that assembly is fundamentally a convenience layer. It doesn't change what the machines can do, but dramatically improves the programmer's ability to write, understand, and debug programs. Grasping assembly is essential because it bridges the gap between human thinking and machine operations, showing how high-level concepts ultimately translate into hardware-level actions. PEP9 assembly language. Here this slide revisits the distinction between immediate and direct addressing, but now in the context of assembly mnemonics. Immediate addressing is marked with I, meaning the operand is the actual data. Direct addressing is using D, meaning the operand refers to a memory location. This simple notation is one of the advantages of using assembly language. You can clearly specify how a value should be interpreted using concise labels rather than raw bits. Understanding these addressing modes is essential because they influence how program instructions fetch or use data. This slide helps begin your transition from machine language structure to readable assembly code, showing how each instruction still precisely controls hardware level behavior. PEP9 assembly language. Slide number 2. Here we see important difference between operations and pseudo operations, also called directives. Operations are true instructions that the assembler translates directly into machine code. Things like loading data, performing arithmetic, or branching, etc. Pseudo operations, however, are not executed by the machine. Instead, they give instructions to assembler itself, often related to memory allocation, data initialization, or program organization. Examples include directives for defining constants or reserving space. Without pseudo operations, it would be much harder to manage memory or structure a program. Understanding these two categories ensures you know what parts of your code produce machine instructions and what parts simply guide the assembly processes. This slide presents a complete assembly language program that outputs the word hi. It illustrates the structure of an assembly program loading character values, using the system output instruction, and following the program with data definition. By studying this example, you learn how each instruction corresponds to a specific task, such as loading ASCII codes for H and I into the accumulator and calling the output routine. The example reinforces the concept that assembly requires you to manage every low-level step, including retrieving data, issuing system calls, and organizing memory. Seeing high produced on screens makes the machine's behavior concrete and shows how small sequences of instructions build real functionality. This slide shows an assembler listing, which reveals how your assembly code is translated into machine language. The listing includes memory addresses, opcode values, and symbolic labels. This output is extremely useful when debugging because it allows you to verify that your instructions and data were placed at correct memory location. You can trace how each mnemonic you wrote becomes a specific machine language instruction. The listing also helps you understand the exact memory layout of your program, making it easier to find errors in addressing, branching, or data handling. Learning to read assembler listing is a vital skill for low-level programmers because it exposes what the machine truly sees and executes. Here you explore instructions for outputting numbers and performing branch operations. Outputting numeric data requires converting values into a format that can be printed, often relying on system routines. Branch instructions let you program make decisions by changing the flow of execution, jumping to different paths of code depending on conditions. These instructions enable more complex behavior such as loops, conditional statements, and error checking. This slide begins to show how assembly can represent logical structures found in higher level languages. Understanding output and branching is essential because they form the basis for interactive and dynamic programs that respond to our user or system state. This slide presents a full program that reads two numbers from the user and adds them together. It blends input instructions, arithmetic operations, and output routines. The program also demonstrates how data moves between the accumulator and memory as values are loaded, manipulated, and stored. This example is important because it highlights the procedural nature of assembly programming. Every tiny step, reading input, storing it, performing addition, and writing output, must be explicitly coded. By studying this program, you learn how assembly interacts with user input, how the CPU performs arithmetic, and how results are printed, all through simple fundamental instructions. Here you see a variation of previous program, but with added logic to detect whether the computer's sum is negative. If the sum is less than 0, the program prints error message instead of numeric result. This demonstrates how branching, comparison, and output work together to implement conditional logic. The program shows how assembly mimics high-level constructs like if-else, but requires more manual control. It also highlights the importance of checking conditions to prevent incorrect or misleading output. The slide deepens your understanding of control flow and shows how assembly programs can become more robust and user-friendly through careful instruction design. In the final slide, we see a program that uses a loop to read sum and sum multiple numbers. The loop structure relies on branching instructions and a counter stored in memory. Each iteration reads a number, adds it to a running total, and updates the loop variable. This demonstrates how repetition, an essential algorithmic construct, is implemented using low-level instructions. The example also shows the importance of initialization, condition checking, and updating variables. By understanding this looping pattern, you gain the ability to write more complex programs that handle sets of data rather than single values. It reinforces how assembly requires explicit control of every detail, yet remains powerful enough to express full algorithmic logic. Pseudocode. Pseudocode is a method for expressing algorithms using a mixture of English phrases and simple structural formatting. It's not a programming language, but rather a clear, consistent way to outline the steps needed to solve a problem. In this slide, we examine a pseudocode algorithm for converting a base 10 number into another base. The steps rely on repeated division, tracking the number remainder at each step, and assembling the digits from right to left. This example shows how pseudocode helps you think through logic without worrying about syntax details. By focusing on the flow, looping, dividing, storing results, you begin to see how an algorithm develops before it's translated into assembly or a high-level language. Following an algorithm, here this slide offers a fun example, preparing a hollandaise sauce using an algorithmic approach. It demonstrates that algorithms aren't limited to computers. They describe any step-by-step process. The algorithm includes conditions, loops, and actions, much like a computer program. For example, it uses an if statement to decide between butter and a substitute, then applies a while loop to keep heating the mixture until it bubbles. Later, it alternates between steps such as blending ingredients and pouring slowly. By presenting a cooking recipe as an algorithm, the slide emphasizes that clear, structured thinking applies to real-world tasks. It shows how algorithms guide decisions, repetition, and sequencing in a predictable and testable way. Pseudocode basics. Here, this slide reinforces what pseudocode is. It's a clear, structured way to express algorithms using English phrases and indentation. There are no strict grammar rules, but pseudocode should always be consistent and unambiguous. It serves as a blueprint for problem solving, capturing the essence of logic before committing to a specific programming language. This flexibility allows you to refine your thinking, clarify steps, and identify errors early. The takeaway is that pseudocode is not about syntax. It's about communicating logic precisely, whether preparing to write assembly, C++, or Python. Pseudocode ensures your conceptual algorithm is solid and easy to follow. Following pseudocode. Here this slide walks through converting the number 93 into base 8 using pseudocode from earlier. The algorithm repeatedly divides the number by the new base, recording each remainder. First 93 is divided by 8 gives 11, remainder of 5. Then 11 is divided by 8 gives 1, remainder 3. Finally, 1 divided by 8 gives quotient of 0, remainder 1. Reading the remainders backwards produces the answer 135 in base 8. This example shows how pseudocode translates into concrete steps that solve problems methodically. By working through this transformation, you see how loops, arithmetic, and data tracking combine into a complete predictable algorithm. Now, this slide includes a detailed visual walkthrough of the base conversion algorithm. The figure illustrates each iteration, the quotient, the remainder, and how digits are assembled into the final answer. Seeing the algorithm mapped out visually helps reinforce how systematic and reliable pseudocode can be. Each steps Each step follows the same pattern: divide, record, replace, and repeat, which highlights the power of iteration in problem solving. The goal is to help you understand not just the answer, but the process that generates it. By breaking the problem into small, repeatable steps, the algorithm becomes easier to code and verify in any language. Pseudocode functionality, variables, and assignment. Uh, in this slide, we see variables and assignments in pseudocode. Variables are simply names representing locations where values can be stored, such as quotient, decimal number, or new base. Assignments places a value into one of these variable locations. The slide offers examples like set quotient to 64, quotient 6 multiplied 10 plus 4. These examples show how pseudocode captures arithmetic operations and updates stored values. Understanding variable assignment is essential because it reflects how computers manage and manipulate data. Even though pseudocode doesn't follow strict syntax, these operations mirror the precise steps a real program must implement. Here we learn about input and output operations in a pseudocode. Output instructions such as write or print display information to the user. Input instructions such as get or read collect data from outside world and store it into variables. These operations enable communication between the algorithm and the user. Understanding how to read and write values is crucial for building interactive programs. In pseudocode, these actions are expressed in simple English phrases, but they map directly to the input-output operations used in assembly or high-level languages. This slide emphasizes how pseudocode models the flow of data into and out of a program. Selection, simple if. This slide focuses on selection, making decisions in algorithm using if statements. A simple example is reading a number and checking whether it's less than 0. Depending on conditions, different messages are printed. This illustrates how algorithms can include optional paths or error handling. The slide also shows how multiple actions may follow a single condition, such as prompting the user again if a value is invalid. Selection structures allow algorithms to react dynamically to user input or program state, making them more flexible and robust. Understanding selection is foundational for implementing decision-making logic in any programming language. Here, we expand on selections by showing multiple if-else branches. The example compares a person's age to determine the ticket price category, children's rate, regular rate, or senior rate. This demonstrates how pseudocode handles multi-level decision making. Each condition is tested in order until one matches. Multi-branch selections allows algorithms to model complex scenarios with many possible outcomes. Understanding this structure prepares you for similar logic in assembly, where branching instructions must be used carefully to replicate these choices. This slide emphasizes clear organization and indentation to keep multi-branch logic readable. Repetition loops. This slide introduces repetition while using a while loop. The example sets a counter to 1 and continues looping while the counter is less than 10. Inside the loop, the program prompts for a number, reads it, and displays it, then increments the counter. The structure shows how loops allow algorithms to repeat tasks many times with changing data. Repetition is essential for processing lists, managing iterative calculations, or handling ongoing input. This slide illustrates the fundamental pattern: initialize, test a condition, perform a set of actions, and update variables. Mastering this concept is the key to writing efficient programs in assembly and higher level languages. Pseudocode example. Here we see a pseudocode problem. Reading pairs of positive numbers and printing each pair in order. The pseudocode begins with a while loop that continues until the task is complete. Inside the loop, the program prompts the user to enter two values separated by blanks. It then reads the first and second numbers. After receiving them, the algorithm prints the numbers in order, meaning the smaller one is printed first. This example demonstrates how pseudocode handles repeated input, conditional ordering, and output formatting. It shows how a simple loop can repeatedly request data from the user and produce consistently formatted results. By examining this example, you learn how pseudocode can structure interactive input processing tasks very clearly and logically. Here on this slide, we expand on the previous idea by addressing an important question: how do we know when to stop? Instead of looping indefinitely, the revised pseudocode introduces a stopping condition determined by the user. Before reading the pairs, the program asks the user how many sets of numbers they want to enter. This creates a controlled, predictable loop count. The slide also clarifies the logic for printing the numbers in ascending order. If the first number is smaller, print it first. Otherwise, print the second number first. This reinforces the idea that pseudocode can incorporate both user control and conditional logic to create well-structured, predictable algorithms. Now, this final slide, the pseudocode is fully developed into a complete algorithm using a loop controlled by a counter. The program first asks how many pairs of values will be entered. It then sets a variable, number read, to 0. The loop continues while this counter is less than the total number of pairs requested. Inside the loop, it prompts the user for two values, reads each number, and prints them in ascending order using if statement. After printing, it increments the counter. This complete example shows how initialization, condition checking, input reading, comparison, output formatting, and updating variables all come together in a single functional algorithm. It's a perfect illustration of structured problem solving in pseudocode. Walkthrough. This slide provides a walkthrough table that shows how pseudocode algorithm works across several iterations. It includes sample value for the variables such as number read, number 1, number 2, and number of pairs, and demonstrates how the change during each cycle of loop. By tracking these values visually, you can better understand how the algorithm processes data and updates internal state. This walkthrough makes the abstract pseudocode concrete, helping you verify whether your logic behaves as expected. Understanding how variables evolve step by step is crucial for debugging both pseudocode and the real programs you will later write based on it. Translating pseudocode. This slide reminds us that the pseudocode is only a planning tool. Eventually, an algorithm must be translated into a programming language. The slide asks the question, to what? The answer is that pseudocode can be translated either into assembly language or a high-level language. Assembly translation is very detailed and time-consuming, requiring careful control over memory and instructions. High-level languages make this process easier by providing abstractions like variables, loops, and conditionals. This slide emphasizes that while pseudocode is informal, it's incredibly valuable because it gives you a blueprint for implementing a correct solution in any programming language. Testing. This slide introduces the concept of a test plan, which outlines how to thoroughly verify a program. A test plan specifies how many times and with that what data the programs must be executed. The slide also introduces two testing approaches, code coverage and data coverage. Code coverage focuses on designing test cases that exercise every possible path or section of the code. Data coverage, also called black box testing, ensures that test cases reflect the full range of allowable input values. The slide leaves you with an important question. What does thoroughly mean? The answer lies in in it lies completely how completely you test your cover both logic and data scenarios. The final slide on testing focuses on implementing a test plan. After designing test cases, you must run through program with each one and verify that actual outputs match the expected results. This step is essential to ensure that your program behaves correctly under all predicted conditions. Test plan implementation often reveals subtle logical errors or overlooked scenarios. It encourages you to validate not just that program works, but that it works reliably, predictably, and safely under all required circumstances. Thorough testing is cornerstone of professional programming practice, whether in assembly language or high-level language. Important threads. This slide summarizes the key ideas about computer operations. First, computers can store, retrieve, and process data, fundamental abilities that make them useful for countless applications. Second, every computer has a machine language, a set of binary instructions its hardware is built to recognize and execute. Third, a machine language program consists of entering sequences of these instructions in binary form. This summary highlights the low-level foundation on which all software is built. Understanding these ideas allows you to appreciate how higher-level abstractions ultimately depend on precise hardware-level operations. Here we summarize the PEP9 environment. PEP9 is a virtual computer with a single accumulator register and instructions divided into two parts, one describing the action and another describing where the data is located. PEP9 assembly language allows programmers to use mnemonics codes instead of raw binary, making programs far easier to write and understand. The slide also ties in pseudocode, emphasizing its role as a shorthand tool for expressing algorithms before implementing them in assembly or another language. Together, these concepts form a complete workflow. Develop the algorithm, express it clearly, then translate it into executable instructions. The final slide highlights the importance of testing programs. Every program, regardless of complexity, must be thoroughly tested before it can be trusted. This slide mentions the two major testing approaches: code coverage, which focuses on exercising all paths in the program, and data coverage, which ensures the program handles all allowable kinds of input values. These methods complement each other to reveal different categories of errors. Understanding and applying both approaches ensures that your software behaves correctly, reliably, and consistently in all expected situations. Thank you for attending the class, and yourself a pat on your back for coming this far. I hope to see you in the next class. Take care now. Bye.